Okay, let's start our first module, module 0. In this module, we will introduce the concept of set. So first of all, what is a set? I'm not going to give mathematical rigorous definition because that will be very complicated and definitely well beyond the scope of this course. So in this course, we will be satisfied with the following informal definition. A set is just a collection of objects. Entities, things, etc. Generally speaking, a set is just a collection of objects that share some common property. Okay, I think the best way to illustrate this concept is by giving examples. For example, I'm using S1 to denote the set of students register this course. And for simplicity, I assume that there are 26 students registered this course, and they are called Alice and Bob, and so on and so forth. And last one is Zoe, because I'm going to call their abbreviation as A, B, C, Z. Okay, we will use notation, very important. Belongs to Alice, belongs to this set. We use this notation, means belongs to. And sometimes we also call this Alice is in the set. And Alice is called an element of the set. Okay. So how do we denote a set? How do we represent the set? The most simple way, the simplest way to represent is called set raster notation. For set raster notation, we simply list all the elements in the set. Okay. For example, I just say S1 equals Alice, Bob, and so on and so forth. And if there are too many elements in the set, I may list just a few leading elements. Okay. For example, S2, I may say 1, 2, 3, and so on. I will denote this set to be I'm thinking about S2 as the set of all positive integers. For example, S3, I can use S3 to denote the set 1, 3, 5, 7, and so on. And you may guess I use this set to denote all positive odd integers. Okay, if there are only finite number, if there are only finite number of elements in a set, then we will use this notation to denote the the sides. Okay, and more formally we call it cardinality. And for example, I would say S1, cardinality of the set. Okay, for example, I would say S1 equals 26. As supposedly there are 26 students registered for this course. Okay, the next concept is we are going to introduce some special set and their notation. Because we are going to use, see this set again and again, some special set and their notation. And first of all, we will use R to denote real numbers. Of course, there are infinite. This set is an infinite set, so we don't talk about the cardinality. Okay, the cardinality is infinity, so we don't talk about cardinality. And usually we just denote it by a real axis. This is 0, and we use a real axis to denote these real numbers. And the next set we usually encounter in this course is Z, the set of integers. Okay, similarly, we use this real axis, but now it's not every element in the set on the axis, but we have this 0, 1, 2, 3, and so on and so forth. Infinity, and then we have -1, -2, -3, and so on. So Z, basically Z is, if we use raster, we use that raster notation, then it should something like this: -4, -3, -2, -1, 0, 1, 2, 3, 4, and so on and so forth. So you can see it's not very convenient to use set raster to write for this set Z. So we use we just use the letter Z, the capital Z, to denote this set of integers. And sometimes we use the plus to denote the set for non-negative. Non-negative integers. Okay, means that means C plus 0, 1, 2, 3, and so on and so forth. And the plus plus to denote the set of positive integers. One, 2, 3. By the way, you probably will see, and probably you have seen this notation of natural numbers. This capital letter N. Natural numbers. Unfortunately, for natural number N, we don't have a commonly agreed notation. That is because some authors use N to denote. Some others say that N is just equal to Z plus. And some use the notation to denote Z plus plus. Okay, the only difference is do you count 0 as a natural number or not? And so usually when you read the paper, you read the textbook, you should be careful which of the notation, which of the two notation the author is using. Both are okay, and many both are used by many authors. Okay. So the question is zero is element of natural number or not? Okay, the next set we are going to talk about is a Q. It's a set of rational numbers. And probably you haven't seen this notion before. And by rational number, we mean that any number can be represented as a ratio, of two integers. Okay, for example, 0.4 is 0.4 is rational. It's a rational number because it's 2 over 5, and minus 0.33333, and this is equals minus 1 over 3. So this is also a rational number. And we are going to see that some number is a real number, but not a rational. Such a number are called irrational numbers. Okay. So finally, C, the complex numbers. For example, 5 plus 3i is in C. Minus square root of 2 plus square root of 3 times I is in C. Okay. So the next topics we are going to talk about is another different notation, because you can see from our previous discussion when we define this integers, the set of integers, the set of rational numbers, set of complex numbers, and it's not very convenient to use set raster notation. So instead, we are going to introduce a more commonly used notation called set builder notation. Set builder notation is just we specify the common property of all elements in the set. Okay, for example, S1, if you remember S1, I can say S1 is any student at FIU register this course. Okay, remember the set raster notation is listing all the elements, and both notation define the same set. Okay, in general, how do we define what is a set builder notation? So let me give you try to give you a definition. So let S be a ground set. Okay, so what does ground set mean? Ground set means that we would to build a set, we don't start from scratch. Okay, for example, in order to define set S1, first I may say this set is about people, or more concretely, I'm talking about students. What student? You, a college student, and more specifically, I'm talking about student at FIU. So this student at FIU is my ground set. Okay, and let S be a ground set, and P X is a property. that all elements in S may or may not share, may or may not satisfy. And then we can define the set is as X in S, X belong to S, and then we use a bar, vertical bar, PX. Okay, so in this, in the S1 set example, clearly S is the set of FIU student. This is our ground set. And what is the property? Property is registered for COT 3100. Okay, this defines a set. Okay, so we can write, now we can write S1 as X is an FIU student, vertical bar, X registered COT 3100. This is just a different, another way of define the set. You're going to see that for many set, especially for infinite set, set builder notation is much more convenient to work with. Let me give you some examples. Okay, so let's see more examples. First, the first example is what is Z plus. So Z plus, now we can define as the set N in Z. Okay, Z now play the role of ground set. Okay, vertical bar N is at least 0. And you can also say, if you don't want to provide, you don't want to use Z as a ground set, and also you can say, alternatively, you can say Z equals just N. And usually we write N this way, means N is a number. Okay. N in Z. And N is at least 0. Okay, by the way, I think I forgot to mention that there's another commonly used notation. Instead of use vertical bar, you use you can use similarly. You can write Z plus and you can use 2 dot. Of course, vertical bar notation is used in the textbook, so we are going to follow this notation. Okay, what about Z plus plus? You can easily see that Z plus plus can be conveniently defined this way: N in Z, Z, and N bigger than 0. It's very convenient instead of listing all the elements, which we cannot do. Okay, the next example is Q. Now we can more rigorously define what is a Q. Q is X in R. It's the first X. It's a real number. So in order to be an element in Q, you have to be first of all, you need to be a real number, and then X equals P over Q, and P Q is in Z. That means X is equal to the ratio of two integers. And the third one is, what about so what is this set? X in R, x squared minus 3x plus 2 equals 0. So what does this set denote? Actually, this is, okay, so first you read x in R. That means x is a real number. X has the property that x squared minus 3x plus 2 equals 0. That means x is the root of this quadratic equation. And therefore, we can, by solving this equation, we know that x actually is using the set raster notation. X S4 just contain two elements, 1 and 2. And similarly, we can define S5 equals x in R, x cubed minus 1 equals 0. So this set a little bit tricky. So we know x cubed minus 1 is contains 3 roots. Okay. But since we for the ground set in this definition, x must be a real number. So we know that we the other two complex root have to be excluded from the set. So S5 basically is just single element, contains single element 1. And similarly, if I write x in C, that is I change my ground set to C, and using the same property, x cubed minus 1 equals 0. And now you can see that S6 actually contains 3 elements because now it's contained two complex numbers, two more complex numbers, which is minus 1/2. If I did this calculation correctly, minus 1/2 minus 1/2 square root of 3 times I. I think now it's the time to do some clarification. And first of all, the element order doesn't matter. And basically, when we say a set 1, 2, 3 is the same set as 2, 1, 3, and 3, 2, 1, 3, 1, 2 are basically the same set. We talk about the same set. And similarly, also, if when we talk about set, we actually talk about belonging relationship. What does it mean? That means when we write set, this set is 1, 2, 3. That means 1 is in the set, 2 is in the set, 3 is in the set. Okay, and therefore, if some element repeat more than 1 times, if you denote denote the same set, 1, 2, 3, 3, 1, 2, and basically this is the same set as 1, 2, 3. Okay. So usually we don't write this way. Okay. We only represent a single element only once. But but if someone uses this notation, then it means the same thing. Okay, this is element order and repetition. Don't count. Okay. As I said, because this set notation just show that 1 belong to this set, 2 belong to this set, 3 belong to this set. And second thing we want to clarify is you need to distinguish between a set and an element. And more specifically, when we talk about number 2, that means this is a natural number. But if we write as number 2 as an element of a set, this denotes a set. So this is a set, and this is a number. They're complete different things. So you cannot talk about they are the same. They are complete different things. And therefore, we may have a set like this: 1, 1, 2, 2, 1, 2. Okay, in this set contains 5 elements. The first element is number 1. The second element is a set, which contains number 1 as the only element. And similarly, the third element is a set containing number 2 is the single element, and so on and so forth. And next thing I want to clarify is empty set. We use this special notation pretty much like a Greek letter phi to denote empty set. It's a very special set. It has some very intriguing property. It means this set contains nothing. Okay, it's a very special set. And we are going to see this set many, many times. Okay, I will stop here for this video. Thank you.